In the excitement, I will tell you truth about our field. And just to wake you up, let me start with some kind of blah, 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 because now everybody loves it, yeah? So, why do we need to study cosmology at all, yeah? The simplest answer is that all of us wants to feel a little bit superior with respect to monkey, of course, but, you know, I love how Steve Weinberg formulated it in elegant and politically correct way, because at the end of his book, excellent book, First 3 Minutes, he wrote, the efforts to understand the universe is one of the very few things that lifts human life a little above a level of farce and gives it some of the grace of tragedy. You see, so I also didn't expect. This is the reason why I am cited. About the level of farce and gives it a grace of the tragedy. But of course, people, let me give you a little bit short story, because cosmology has really very short story. Because till 1990, it was some kind of natural theology, not theology, it was natural philosophy. And after 1990, it became natural science. And you know what is the difference? Difference I learned from some guy whom I know who is a Jesuit priest, because when he told me, oh, cosmology is natural philosophy, I told him, what do you mean? He told, oh, natural science is solid state physics. I told, guys, okay, people in your church forgot to upgrade it, because about 2000 it already was a natural philosophy, but natural science, yeah, sorry. But in fact, actually, of course, people were discussing the origin of the universe since long time, and I think here is the right place to quote Kabbalah, yeah? So, because I think first quote which I got from Sid Bladman was from Kabbalah, from the Zohar book, where it's written that God creates new worlds constantly. But 2 months ago, Francois Engler told me a fantastic story, which he also found in Kabbalah. It was translated for him by his friend, yeah? So, where it's written about creation of our universe, like this one, that God was borrowed, and then he decided to create universe, okay, to make life a little bit more exciting for himself, but then he immediately faced with a trouble. He found that he occupies everything, you see, and there is no place for creating universe. It's the real story, yeah, from Kabbalistic text. So, therefore, he thought a little bit, then he shrinked himself to the point, and in remaining space, he produced universe. But then he expanded and found that universe which he produced is a little bit too boring, because it's too symmetric. But it's not concretized in Kabbalah. Was it Minkowski space, anti-de Sitter, or de Sitter? Now we know that it was de Sitter, which, by the way, do not so-called evolve, right? Then he thought a little bit, shrink himself again to the point, but before shrinking, he distributed a little bit garbage around, and this garbage we know now that it's quantum fluctuations. Then he again created universe, then quantum fluctuations or garbage spoiled the exact symmetry, and then he discovered himself. Why I said itself? Because I had discussion. If I go to America, I should use he or she. You see, and it was undecided, by the way. I discussed it with Pierre Ramon. He could not give me unambiguous advice, yeah? So, and then, you see, after that, it's formulated in Kabbalah in the following very nice way. Only by their breaking could the divine configuration be perfected. You see, because after that they became alive. Now, of course, history of cosmology in the sense of natural philosophy go far away in past, because even Archimedes, who always tried, not just blah, 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 yeah, to get numbers, managed to estimate the size of our cosmos. I think he got something like 2 light years, so very wrong. But then in 8th century there was Hindu-Puranic cosmology, which estimated the age of our universe as 4 billion years. Not very wrong, by the way. Then, as you understand that, okay, only recently, as you will see, it became clear that this nebula, which Messier had in his catalog, I think about 140, some of them are different galaxies, okay?
How did he estimate 4 billion?
4 billion, not he estimated. It was Hindu-Puranic cosmology. I have no idea what these guys were doing, you see, and I just found this thing in Wikipedia, but of course we know that we should not trust Wikipedia also, right? So then Immanuel Kant, by the way, was one of the first guys who assumed that some of these nebulae are really separate universes or separate worlds. Now we know that, okay, it's separate galaxies. But then Newton was thinking about it, Descartes also, what is the universe, but I think, okay, 1916, when Einstein invented general relativity, as David explained you yesterday, he immediately tried to apply it to universe. And he had great idea, which now is known as cosmological principle, that universe in large scales is homogeneous and isotropic. But Einstein wanted more than homogeneity and isotropy. He wanted also time translation invariance. This is the reason why he introduced cosmological constant, which some people, okay, tell that Einstein said it was his greatest mistake. In German it sounds, as Einstein said, that it was my greatest SLI. You see, stupidity, which is more correct actually word, yeah, for this kind of thing. But you know that after that, but you know that the real cosmology started perhaps since 1923 when Edwin Hubble, yeah, using this Mount Wilson telescope near Los Angeles, managed to identify in Andromeda separate stars. And then because it was the stars with so-called variable stars with the known luminosity, he managed to estimate the distance to this Andromeda. And it was the first time when actually it was shown, really proved, that Andromeda is outside of our galaxy. Around 22, 24, so you know that some Russian, I don't know, okay, in America people call him mathematician, Friedman, yeah, but I think from mathematics the only thing which he has is degree from mathematical department. In fact, he was meteorologist. And moreover, he was even doing experiment, you see, in meteorology. And in Russia, there is a medal, Friedman medal in meteorology, first of all, but not in cosmology. He actually found these non-static solutions of Einstein equation, as you know, and I don't know how he managed, because at this time, of course, it was not known that in our galaxy is, perhaps this thing was known that it's about 100 billion stars, but was not known that there are 100 billion galaxies in the universe. But nevertheless, for some kind of reason, he took mass of the universe 1055 gram. I do not know how he managed to get this number and got even age of the universe approximately correctly, 10 billion years. Then also at a little bit before, De Sitter found some solution where if you would take geodesic equations, then of course all geodesics are escaping from us. And this solution at the beginning people tried to use to interpret redshifts. But at this time actually the redshifts which were discovered, it was not clear. Some of them were extragalactic redshift because of the Hubble expansion, the other were okay, because of the peculiar motion. And the guy who, by the way, first time realized that De Sitter solution describe also expanding universe was Lemaitre. In 1925, he has rewritten static solution and expanded flat coordinates, as you see. But then the solid basis cosmology got with so-called Hubble discovery of Hubble law, because using some standard candles, he was able to measure distances to the nebulae, okay, which he thought are galaxies, And simultaneously, because the spectral lines were redshifted, he interpreted it as Doppler shifts. Therefore, he was able to measure velocity. And the graph which he got was like this one. But nevertheless, he managed to draw straight lines through it. You see? And, of course, you can write V is equal h distance r. He managed to measure this distance, and he got about 500 kilometers over second over megaparsec. Now, if you will take this distance divided by speed, okay, then forget about gravity for a minute. It doesn't give too much. Yeah. Then you will get that the age of the universe in this case would be less about 1 billion years, but it was clearly in contradiction with the age of the Earth, not universe at this time. But of course, and the main thing actually why he made mistake was this distance which he used which he determined using so-called standard candles. You assume that you know luminosity of some object, but luminosity in astrophysics is always subject of so-called systematics. As I say, when systematics is gone, then you can skip astra, and astrophysics becomes physics. You see? And in fact, I recall that in 1980, already there was improved measurement of the Hubble constant, but one group, I think Vaculer, was given 100, and the other Sandwich and Taman were given 50. Theorists at this time, they didn't know to whom to trust, therefore they were taking 75, and as usually they were most close to the real truth, because now we know that it's about 67, 68. So, but it's actually now determined from CMB. Now everything actually is done from CMB. Then also in 30s, Zwicky, I will not quote him because he has a nice sentence, okay, about astrophysics. He managed to identify, okay, clusters of galaxies. But even in 80s, not all astronomers believed in these clusters of galaxies, because some of the people, very respectable astronomers whom I knew, were telling me that no, it's not clusters of galaxies, but because we see two-dimensional picture of the sky, it's just galaxies which are far away from each other but came to the same sight line, you see? And there are maximum double and triplet of galaxies. But of course now we know that these guys were not right, because cosmological principle, which was principle for very, very long time, finally became established fact. And you know when it became established fact? Only in 2001, when Sloan Digital Survey published the redshift of 1 million of galaxies, and then we got the possibility to distribute all these galaxies in the space. So, because if you know redshifts, then you can know the distance. And then what we discovered that our universe has so-called large-scale structure. So galaxies normally are clustered in the clusters of galaxies. Then clusters of galaxies are connected to filaments, where the density of galaxies is less than in clusters of galaxies, but larger than the average density of galaxies in the universe. Filaments are connected by walls, and between walls there are big voids. It's so-called web structure of the universe. However, if you will take boxes with the size 100 or 200 megaparsec, smear the matter, then you will find that in these scales and larger scales, the universe is still homogeneous and isotropic. So, one of the things which was established in by 80, let me say, by 80 was Hubble expansion, in spite of the fact that there were a few guys who tried to interpret redshift in a different way. The other important piece, experimental piece, to our knowledge about universe came in 1965. Okay, it was some kind of accidental discovery by Penzias and Wilson of the microwave background radiation. They tried to remove noise from their radio antenna, which was about 3 degrees, but were not able to do it. And then, as far as I know the story, but Jim Pimps, who will be here, knows this story much better, because at the same time, he, Wilkinson, Dickey, and fourth guy, engineer, I forgot his name, yeah, okay, you can ask Jim, yeah, were preparing experiment to discover this radiation. And it was not, how to say it, so unexpected in some sense, because in 40s, at the end of 40s, Gamov, then Alper and Hermann, also Fermi and Turkevich, were trying to explain the abundance of the chemical elements in our universe. And we know that in our universe, 75% of all elements is hydrogen, 25% is helium-4, and you could ask where we are really in very trace amounts. But, of course, how could you explain the origin of helium? You could say that you produce it in the stars. On the other side, you know the age of the universe, as I said, like 10 billion years. You know the binding energy of helium. And then when you would calculate the luminosity of sky, assuming that you are producing this helium during the last 10 billion years, and you would get that this luminosity is 100 times more than we see in reality if you would produce helium in the stars. Therefore, the only way to produce helium was to make it in the very early universe when temperature was extremely high. Then you explode at this high temperature a lot of hydrogen bombs, roughly speaking. And at high temperature, nobody even cares about these bombs explosion because they are unnoticed. And then after that, you cool down this radiation. This was the idea. In fact, I do not know how these people managed to get 5 degrees, okay, estimate, considering abundance of helium, because, of course, accuracy was not so good, and even now from helium abundance, you cannot predict this number. But they got 5 degrees, and when Gamov was giving interview to BBC, he forgot that they got 5 degrees, and he said 3 degrees. I do not know actually again how he managed to do this thing, because I was writing recently some paper, I wrote that it looks like some Russians perhaps had direct telephone line with God. But then Steve Weinberg was upset a little bit, and he told Alper and Hermann are not Russians. In fact, actually, they are also coming from some village in Russia. Okay, good. Now, then, what happened? Actually, in 1980, we had 1.5 established fact. Why? Because we knew that universe is expanding. Second thing, that there should be cosmic microwave background radiation. But people were not sure that this cosmic microwave background radiation, okay, was primordial radiation. Moreover, I recall in the 80s, okay, Martin Rees was writing paper where he tried to explain this radiation as emitted by some superstars when universe was 1,000 times smaller. And he was claiming that after this radiation was thermalized on dust. It was not excluded. To exclude this thing, in fact, actually what one needed to measure the Planck spectra of this radiation. You see, it should be like this one. All measurements which Penzias and Wilson did were referring to this region. You see. Now, here in the region of higher frequencies, which correspond to a millimeter, etc., atmosphere was not transparent. Therefore, either you needed to go, okay, up on balloon. Now people, by the way, found the way how to measure it there, even because there are windows of transparency. But at this time, nobody knew about it. Or to go outside of our atmosphere using some kind of space mission. In fact, 1987, there was so-called Berkeley-Nagoya experiment, which showed that the spectra is not thermal spectra, and it would be the end of cosmology. for physicists, not for cosmologists who are doing it professionally, because for them it will never be end, you see, if it would be correct. But in fact, what was discovered after that, they had systematics, and the spectra with very high accuracy in this region of the first Doppler peak, I think, was measured by COBE satellite on the device for which principal investigator was Mather. And accuracy here, which he got, was so unbelievable. When they draw these experimental results, they show a row bar 400 sigma. You see, if you would show 1 sigma, you would just see the point which are perfectly on theoretical curve. And okay, it would look like lab done by very bad student who forgot about error bars, yeah, when he was falsifying the results. You see, but now it's actually fact which is no doubt about it. The other thing, but it happened 1992 when cosmology, in fact, as natural science, studied with this COBE satellite, which made the other discovery, which was foreseen already. People in 70s, when people, Shunyaev, Zeldovich, were writing paper, okay, telling that to explain large-scale structure, this background radiation, which has, okay, according to the current experiment, the same temperature in different direction, nevertheless should fluctuate. So temperature should vary from place to place by the amount at least 10 minus 4, 10 minus 3, you see. But these kind of fluctuations were discovered for the first time by COBE experiment. Again, principal investigator for this discovery was Smooth, you see. So it was a great thing. After that, in the 90s also, people started to build telescope, good telescope, like crazy. Before that, there was no good telescopes, in fact. One of the greatest telescopes was built on Hawaii, 2-meter telescope, Keck telescope. Then, you know that Hubble telescope was launched, 2-meter telescope. Then, European Southern Observatory built a lot of telescope in Chile. They have, for instance, 4 telescopes, which are working like 1 telescope each, of which 8 meters, which they called very large telescope. And they are going to build next telescope, but perhaps they will call it extra or super large telescope, because in this sense, Europeans have not so much fantasy in naming these things, you see. Now, also, so people also started to do this experiment. So they took 2-meter telescope, and the only purpose of which was to take redshift of the galaxies. And they made this catalog about which I actually mentioned, so-called Sloan Digital Survey. You see, 1 million galaxies. So finally, cosmological principle was established. But at the same time, after COBE, they started the era of so-called precision cosmology. People started a lot of ground-based balloon experiment, and moreover, 1996, 2 application for MAP, which became WMAP experiment, actually where the main person at the beginning was actually Wilkinson, but then he died 2003, I guess. And the other leading person of the experiment was Lyman Page, of course, and Bennett was principal investigator this time, not like previous time, yeah. So then Planck experiment was also approved the same year when they put 2 devices, low frequency and high frequency instrument, on the same rocket. One device was done, and major contribution was Italian contribution, the group led by Mandalesi, and the other device who were responsible for it, French. It mostly, and principal investigator was Jean-Luc Pouget. But this, okay, launch of this Planck was postponed. I don't want to go to all this kind of money detail, but the whole thing actually, I mean, rocket was launched only 2009, you see, and the first result were delivered only 1 year ago. This year there was supposed Second, delivery of the maps of polarization. In fact, they are already, but BICEP, about which perhaps you have heard, spoiled all the plans. Okay, made people first very excited and then very depressed, as you understand. But this thing I will consider later also. So don't worry, I will not forget about this BICEP because it also got on my nerves quite a lot. Now, and you know, now actually what we know the following established fact about universe, and it's not so little. Also, by the way, I forgot to say about other couple of things which people got not from CMB but from telescope. One was this kind of discovery of dark energy with supernova, but the real proof, of course, of the existence of dark energy was again CMB, because without CMB, even people from these teams agree with me, nobody would believe them. Because it could be dust, it could be variation of luminosity or whatsoever. Second thing, actually, baryon acoustic oscillation. So in homogeneities in the scales larger than 100 megaparsec were found. Also, perfect agreement with our expectation. One more thing also which was found with the help of telescope is so-called dark energy, dark matter, because you needed this thing to explain the virial structure of the clusters of galaxies. Otherwise, it would be impossible to do this thing. Again, first estimate for the amount of this so-called dark matter were done based on the virial theorem, perhaps by Jim Peebles in the 80s, but people were never able to get more than so-called omega 0.3 in the form of dark matter which should be there for virialization of these clusters. And first idea about existence of this dark matter belongs to Zwicky, to 30s, who was also thinking that you need to explain the stability of this cluster, some amount of dark matter. Then now, what we can say, okay, using all these kind of experimental facts which were obtained since 90, only since 90, we can say for sure that universe expands, and it's age 13.7 billion years. Okay, here I don't remember exact number, but who cares about extra couple of 100,000 in this case. Then we know that on the large scales it's homogeneous and isotropic. On the scale larger 200 megaparsec today, and has web-like structure on smaller scales, which I just described. Now, we know also, but this we know for very long time, that there is thermal radiation. It's about composition of matter. Thermal radiation with the temperature 2.73 degree, here a couple of signs more. And this, we know that, okay, it has primordial origin right now for sure. When we see this spectra, which is the most perfect spectra, Planck spectra in the nature, there is no doubt about it. Of course, we also know that there are baryons in our universe. This thing I should not prove you, right? And there is one baryon approximately per 10⁹ photons. You see, because in average per 1 cubic centimeter we have 400 photons. Primordial photons. Okay, here much more. Now, also we know that this baryonic matter, okay, has some kind of chemical composition like hydrogen is 75%, helium-4 is 25%, and the rest, very small amount, okay? But one of the things which I want to stress and which is extremely important, and this thing also can be produced only in early universe, is deuterium at the level 10⁻⁵. Why it cannot be produced in the stars? Because binding energy of deuterium is so low, it's 2.3 mega electron volts, that in the star maximum what you expect, because it's destroyed, 10 minus 11. The only explanation for this abundance is primordial nucleosynthesis, which is one of the greatest achievements of cosmology. And by the way, during last several years, this number was established not only with the help of CMB, but also by direct measurement, okay, which Max Pettini did on this Keck telescope. He managed to find the clouds which were virgin, in a sense, very clean, from the dirt which was produced as a result of the explosion of supernova, and he managed to establish the abundance of deuterium with the accuracy which is comparable with the accuracy which CMB gives us. For instance, when you determine the amount of baryons, from which this kind of stuff depends very much. Now, the other thing which we also know, but about which we were not sure for a very long time, that baryons in the whole budget, energy budget of the universe, contribute only 4%. Here, I can be maybe not so exact in the numbers, but you know, 4.5, 4 doesn't matter really, okay? It's not so important. And remaining 96% is dark. Moreover, we know that this dark thing has two subcomponents. One is so-called cold dark matter, and the other is dark energy. What is the difference between cold dark matter and dark energy? Cold dark matter has pressure equal to 0 from the point of view of general relativity. We are all here, by the way, in this room, are pressure at dust from the point of view of general relativity, because energy density is much larger than pressure, with exception of one guy in this room, which is light. Of course, for light, pressure is equal energy density over 3. So it's relativistic component. Dark energy is so-called relativistic component with equation of state pressure, let me write, approximately equal minus energy density. Because if I would write here exactly, then immediately I am in trouble, because Andrei Linde will come and that in this case all of us should be Boltzmann brains. I told him, okay, write approximately, and then you are not Boltzmann brain. I prefer this way. Because he would say that it's eternal de Sitter, and the eternal de Sitter probability of getting us as a fluctuation is much larger than probability to be born by mothers and fathers. Yeah, you know this thing. It's not actually a joke, unfortunately. Okay. No, literature is full by this nonsense. What can I say? And even New York Times writes sometimes papers, cosmic brains with subtitle, have cosmology lost their owns. Overby wrote this paper, you perhaps know. Then, the things which we know that also our universe at the given moment of time has Euclidean geometry today. You see, it could be, as we will see in a minute, either sphere or hypersphere or pseudosphere, but nevertheless, geometry of our universe is the simplest one, and this thing is also robustly established. Also, what we have in addition, super precise picture of the universe, direct photograph, when it was only about 300,000 years old, 400,000 years old, and this picture is delivered to us by so-called primordial radiation, because at this time, when universe was so young, has 400,000 years old, this radiation decoupled from the matter and was propagating to us without significant scattering and delivered us this direct photograph. And we know quite detailed features of this photograph. For instance, we know that at the time when the universe was 400,000 years old, in the universe were, as I call, embryons for the galaxy formation. small inhomogeneities in the energy density from place to place, because more energy density you have, higher is temperature from this place coming. And these kind of inhomogeneities from which all this web-like structure originated had amplitude about 10 minus 4. Epsilon is the energy density. Moreover, we were able to discover that these inhomogeneities are so-called originated from adiabatic fluctuations. It's with very high accuracy. There cannot be more than 1% of contribution from some exotic things like cosmic strings, textures, whatsoever, entropy perturbation. We know that they are perfectly Gaussian because these inhomogeneities introduce fluctuation of the Newtonian gravitational potential at the level of 10 minus 5. And we know that, okay, this is so-called random Gaussian field. And we know that non-Gaussian contribution to this quantity cannot exceed more than some factor phi multiplied by 10 minus 10. You see, it's unbelievable accuracy, but what one can do, okay? We are there right now. And it's, by the way, perhaps the final story, because better you cannot do with CMB because you have finite sample of the things within observable horizon, so-called cosmic variance, when you are bounded by the presence only finite number of realization of the random Gaussian process. And now we are on the border of this accuracy. Moreover, now the measurement of CMB has systematic which is less than these uncertainties related with cosmic variance. Is, I think, okay, so you cannot go further anymore. Now, moreover, we were able to measure how gravitational potential at this moment of time depends on the scale. And we were able to prove at the level of 6 sigma, which will become 9 sigma in January, okay, that the spectra of the fluctuation depends logarithmically, gravitational potential depends logarithmically on the scale. So, moreover, its non-trivial logarithm means the following sense, that larger is the scale, a little bit larger is the amplitude of gravitational potential, and if you will go far away, beyond horizon scale without thinking, then you could expect on the very large scale, universe becomes again extremely inhomogeneous. Here, by the way, growth of the amplitude of perturbation with the scale is completely unexpected on any general ground things, but actually very easily explainable things, okay, by experiment, and this I will discover. Because this logarithm normally is measured within scales which are changing by factor 10, and then in this interval, this logarithm can be approximated as scale in some power 1 minus ns. You see, if you will take this logarithm and then calculate for the scale which corresponds to galactic scale what should be ns, prediction was from 81 that it should be 0.96. And now it's discovered that it's 0.96 plus minus 0.007. And this 0.007 in January will become 0.042. Using, by the way, EE and TE correlation functions for polarization. But this I will explain. So this is the current state of the affairs. And of course, the final purpose of my lectures will be to prove to you that we are all originated from quantum fluctuations, or as our priest said once, okay, what you want to tell me? We are coming from nothing, from shit. I told him, no, quantum fluctuations do not smell. You see, because they have no energy for that. But nevertheless, okay, my final purpose will be to prove that the reason which explains the stability of hydrogen atom is the same as the reason which explains the existence of the large-scale structure of the universe. And this thing actually can be, I think, proved somehow rigorously, because if you will take this theory of quantum fluctuation, it makes 4 robust predictions, and then all these predictions, if any of them would fail, okay, then you could forget about the whole theory. This was my attitude. But last year, okay, all of them passed all the possible tests. This year, okay, appeared this bloody bicep, which nearly killed the theory of quantum fluctuations. Why? Because immediately when the things actually were released, I gave interview, but of course not New York Times, but Süddeutsche Zeitung, which nobody reads, yeah? And besides of German. Now, and then I said there immediately that there are 3 guys, Planck, bicep, and theory with capital Z. And 3 guys cannot coexist together, you see? Because, of course, if you could take Planck and bicep, claims that both are true, then there are these great series who would add couple of terms, 3 more parameters, and would fit you everything, as you understand. But in this case, theory lose any predictive power and it becomes rubbish. Who is interesting only to the people who are writing paper and getting citation for that, but not to anybody else. So I say that 1 out of 3 guys should die. Okay, and fortunately, my bet was on bicep, and fortunately, bicep died. In spite of the fact that Eliezer said that it's a pity, but you see, it would be disaster if this pity would not happen. And you see, because at this point, I always tell experimentalists try normally to prove that theory is wrong, and they are happy to prove that the theory is wrong. For instance, okay, when they found so-called running spectral index WMAP, Lyman was so happy. I told him, Lyman, what to be happy about? You will not repeat this experiment many times. And now, after you got running spectral index, your measurement becomes the set of points which we do not know even what do they mean. You see, I think now they realized a little bit that in cosmology, confirmation of the theory is much better than disprovement of the theory, because if they will disprove the theory, then both we and they will become equally useless. You see? In this sense, okay, people are moving in the right direction. But right now, also in Planck team, I found a little bit disappointment, because theory works so perfectly well. And even there are no anomalies. All these anomalies, they are standing on the ears to get, and they know very well that for these anomalies, they should not blame cosmology, they should blame astrophysics. You see, which is, by the way, much more easy victim, as you know. And of course, Planck will learn a lot about astrophysics, but you know, astrophysics perhaps is not so exciting as cosmology, but you know that what one can do, okay? We do what we can. Now, unfortunately, from this blah, 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 I have to go to the formulas. Because, you see, as usual, I have to start with this simple thing, which is called Hubble law, but some people, Friedman, Robertson, Locker, Lemaitre, universe, but unfortunately some people start to work in cosmology without spending time to learn elementary things, which I think, okay, is not good thing. So, how to describe homogeneous isotropic universe? What kind of spaces do we have which are homogeneous and isotropic simultaneous? First of all, does homogeneity mean isotropy? Of course not, because we can live in homogeneous space which can shrink in one direction and expand in 2 others. Does isotropy means homogeneity? At one point, not, because we can live in the center of spherically symmetrical distribution. Because isotropy at each point means homogeneity, but isotropy at each point sounds a little bit ugly. Therefore, I will use homogeneous and isotropic universe It's universe which at each given moment of time at large scale has the largest group of symmetry, 6-parameter group. Okay, rotations plus retranslation. 3 rotations, retranslation. How to describe this universe? Just to get in a natural way to this description, let's consider 2-dimensional analog. And what kind of spaces do we have which are homogeneous and isotropic in 2 dimensions if we don't care about complicated topologies? First of all, plane. Second thing is sphere. And the third one I will get in 1 minute. But let's start with sphere of radius A. And then let's write the distance between 2 points on the surface of the sphere, imagining that we are 2-dimensional animals who do not see even 3rd dimension. Then this distance can be written in spherical coordinate like a squared, radius of the sphere, d theta squared plus sine squared theta d phi squared. For the further convenience, let me change notation. I hope that you will not object if I call theta high, and I will call phi theta. No objections, right? It's for my convenience. Now, second thing, what is the distance, again, in the angular coordinate on the plane? You could write this as d high squared plus high squared d theta squared. Here, if you want, you can write also a squared, but you understand that this a squared can be also always absorbed with the help of redefinition of high. Here it cannot because there is sinus. What are the other spaces? Of course, everything what you can get are from these 2 metrics. And how to get the third case? You just go from high to I high. Then you get minus here. You get minus sine hyperbolic here. And you have d theta squared here. General minus doesn't play any role. And the third case which you are getting is so-called the case of pseudosphere, or if you want, Lobachevsky space. And because minus appears here, these people call pseudosphere. You see, it's with radius, which is... This thing cannot be imagined by embedding in the space with Euclidean metrics, 3-dimensional space. If you want, you can embed it in 3-dimensional space with Minkowski metric, but I think it's not very illuminating. So will be one more picture, okay, without any use. Now, how to generalize this metric to 3-dimensional case? Very easy, okay? You just write, instead of this d theta squared, d omega squared, and here d omega squared, where d omega squared is the line element on the surface of unit sphere, which is d theta squared plus sine squared theta d phi squared. Now you see the reason for my renumeration. You can go to the other coordinates and you can introduce, for instance, coordinates r, which is by definition in the first case is sine high, in the second case of plane is high, in the third case it's sine hyperbolic high. Then, okay, from here you can express d high in terms of dr and r, and in particular, for instance, d high squared here in this case when you have sine will be 1 dr squared divided by 1 minus r squared. In second case like this one, and in the third case will be plus. And then you are writing metric on the surface of the 3-dimensional sphere, which you embedded in 4-dimensional space or distance, like this one, dl squared, okay, 3D sphere is equal dr squared 1 minus k r squared plus r squared d omega squared. And here a squared, which is the radius of sphere or pseudosphere squared. K takes value 0 plus minus 1. 0 is in the case of flat plane or flat space, plus 1 for the case of three-dimensional sphere, and k minus 1 for the case of pseudosphere. Now, you could ask next question, how this homogeneous space could evolve preserving homogeneity and isotropy. Look at the sphere. The only ways to preserve homogeneity and isotropy and make space evolving is to make radius to be time dependent. You cannot deform the things, only radius, okay, can change there. In this case, how we are describing this evolution of the space? Take two guys on the surface of the sphere, okay, at point A and B. And let's say that angle here is theta. It's clear that when sphere is expanding, blowing up, angle is not changing, and distance between A and B is equal radius multiplied by theta. Let's calculate what will be the relative velocity. Relative velocity A with respect to B will be time derivative of the distance AB, which can be written down as A dot over A multiplied by A and theta. Why I multiplied and divide by this thing? Because A multiplied by theta is distance, and A dot over A people call Hubble constant. Of course, it's not constant, but in our time it's changing on the scale of 10 billion years. So for us it's constant for our lifetime. And of course, you are getting that the distance between 2 points is what is called Hubble constant multiplied by distance between these 2 points. Now, the whole thing is generalized very easily for the case of three-dimensional space, because in this case you can write dAB, which becomes vector, as radius of the sphere multiplied by vector h high AB, which is called co-moving distance between 2 points. Then repeating the same thing, you are getting what is called Hubble law, which is the only law which in principle can preserve homogeneity as isotropy of the space with time. There is no other thing. A is called scale factor. In case of flat universe, it has no absolute meaning because, okay, it can be, as I said, rescaled here. It has only relative meaning in the sense that when it's changing by factor 2, plane is stretched, and those distances which you have drawn, for instance, on the piece of rubber, are growing by factor 2. But in case of so-called sphere and pseudosphere, this A has absolute meaning of the scale of curvature, three-dimensional curvature at the given moment of time. Now, by the way, as I said, now it's experimentally proved that K is equal to 0 with accuracy better than half of the percent. It's the last result, which are really fantastic from Planck, again from 3 curves. Now, next thing, of course, when you are describing evolution of this thing, you have to go in principle to general relativity because you understand that distance is not invariant. Therefore, you have to write what people call interval. And in this kind of coordinate system, which explicitly respects homogeneity and isotropy of the space, of course, you can go in the arbitrary coordinate system. In principle, you can describe even motion of the planets in the coordinate system of the acrobat in circus or in Ptolemy system, but nobody needs it, as you know. Therefore, let's use this kind of adapted coordinate system. And in this coordinate system, interval is clearly equal to difference between so-called proper time of each point minus distance between 2 points. So you could write it as a squared, which now became as a function of time, dr squared 1 minus k r squared plus r squared d omega squared. So you see, this simplest interval describe evolution of homogeneous and isotropic universe. The only complicated thing to understand about this interval is its name. It's called Friedman, Lemaitre, Robertson, Walker, and some people, okay, suggested to add even Einstein. Honestly speaking, I do not understand why you need to use so complicated name for the element of the sphere. Especially, okay, it was at the time of Cartan. Some people tell that it was difficult to make coordinate transformation, but you know, it's always, okay, like this one. Some people from the street never heard even about coordinate transformation. But for normal people, of course, it was not difficult to make this coordinate transformation. But if you want to read the history of the name, you go on Wikipedia, and you will enjoy by this last part. But I don't want to quote it because it will be politically incorrect. Now, okay, so geometry of the space is completely described. What is the other element which we need? Matter, because matter, as we know according to Einstein, determines geometry. How to characterize matter? In cosmological scale, fortunately, we should not even think about particle physics, because everything is describable there by energy density. And, of course, you need also pressure, because pressure, as we know, also contributes to the gravitational field. Normally, people give function pressure. How does it depend on energy density? And this function is called equation of state. To know this equation of state, you need macrophysics. But it's the only place when you need macrophysics. Otherwise, pressure and energy density and four velocities are enough to describe everything. And in fact, actually, this thing should be determined now, and scale factor should be found as a function of time. It's again very simple exercise. Okay, of course, you can take energy momentum tensor for what's so-called ideal fluid, which is epsilon plus p u nu minus p delta mu nu. Substitute it to the Einstein equation, then get all this Einstein equation. But I think, okay, it's too cheap way to get Einstein equation if you want also to gain some physical intuition. Therefore, let me go back to Newton times, use one thing from general relativity and derive equation for Friedman universe in the case when Newtonian approximation we expect should be exact. When it should be exact? When all velocities are much smaller than the speed of light. And by the way, I will be putting in many cases all constant to be equal 1. I hope you have no objections, even gravitational constant, because I don't want to use chalk for nothing. Yeah, so, and, but sometimes I will keep the speed of light. And second thing, pressure should be much smaller than energy density. Also, you understand why you need this condition. Because as we will see later, pressure contributes to gravity. And second thing, if pressure is relativistic, you have some gradient, it immediately actually produces relativistic velocities. You can forget about Newtonian gravity. Then now let's consider infinite homogeneous distribution of the matter. Then if you would calculate Newtonian potential, in this case, you would get infinity. But here you have to be smart, and you have to use what is called Birkhoff theorem from general relativity. Make little hole here and remove all matter. Then according to general relativity, what will be metric inside? Flat, of course. This means that all this matter around could be safely removed, and my ball could be filled back to the same matter. Then let's take radius of this ball to be equal a multiplied by height, according to the Hubble law. Okay, what I wrote before, phi is so-called analog of the angle. And let's write Newton equation of motion for some probe particle of mass m. So mass multiplied by acceleration, let me skip vector things. Okay, dt squared is equal minus, let me write Newtonian constant for the last time, mass inside the ball multiplied by this mass of the probe particle divided by radius of the ball squared. Now what I will do, I will multiply it by 4 pi over 3. Here I will make a cube. Here I will write a and 4 pi over 3. Now what is this? Mass divided by volume, it's energy density. Now you see here it's linear in A, here is linear in A. This mass, I am sorry, is cancelled. Therefore, phi will be cancelled, and you will get immediately equation, which will be A 2 dot is equal minus 4 pi g over 3 energy density multiplied by A. Now, second equation is the equation for the conservation of mass, because here I assume that pressure is much smaller than energy density, therefore this mass is conserved. And from here I see immediately that energy density, which is proportional to the mass divided by A cube, 1 over A cube or 1 over A cube, just conservation of mass. Okay, from here, what I will do, I will just take this integral of the equation of motion and differentiate it. I do some stupidity, but you will see in a minute why I need it. If I will differentiate this energy density, then I will get that epsilon dot is equal to minus 3h epsilon. Yeah? So now h here is so-called Hubble constant A dot over A. Now I have two equations. You could ask me how these equations will be generalized in general relativity. Okay, you can write Einstein equations, and you will find that the rule for their modification is very simple. Here you have to add 3p to energy density, because pressure also produces gravitational field. And here energy density should be replaced by energy density plus pressure, because in fact this equation could be understood also as the first law of thermodynamics. Change of the energy within the ball is equal to the pressure, which is equal to the work which pressure is doing. If you substitute here A cube, here A cube multiplied by energy, then you will see immediately this equation. Of course, it's a joke to say that it's derivation from the first law of thermodynamics, but it also follows from Einstein equations. Now, this is generalization of so-called Friedman equation, or what to say is equation for the universe, for relativistic case. But nevertheless, you do not see here any geometry. And you should not see any geometry, because what we did, we started with flat space, derived something, and then just introduced the pressure. Where is geometry, you could ask me. Well, these two equations are enough or not enough, because there are two equations for two variables, in fact, because pressure as a function of energy density is given. Let's do the following exercise. Let's take this equation, multiply it by A dot, and then use also this equation to find the first integral of this first equation. Then this first integral will look like this one. H squared plus constant of integration divided by A squared is equal 8p g over 3 energy density for an arbitrary pressure. You see, this constant of integration from these two equations, of course, can be arbitrary. But on the other side, you understand that if k is not equal 0, then I am sorry, A has the meaning of curvature. You see? And if you want to have it as a meaning of curvature, and if you will take now 0, 0 Einstein equation, which is constraint equation, so-called constraint equation, So it means that it should be satisfied at one moment of time, and after that it will be satisfied automatically on all equation of motion. Then this constant is fixed to be k, which is equal 0 plus minus 1. In this sense, I am directly relating the properties of the universe or geometry in the universe with the properties of the matter in the universe. Now, you could ask me how we can determine what is the geometry of our universe. It's very easy to see this from this equation. Just rewrite it in the following form. K divided by A squared is equal 8pg over 3 energy density minus 3 over 8pg, here h squared. I'm sorry, okay. First, it doesn't move, but okay, yeah, let me clean. So, now, this quantity has the same dimension as energy density, and it's called critical energy density. Is the energy density which would describe kinetic energy of the Hubble expansion of the universe. And then you see that if you would measure Hubble constant, okay, using this kind of Hubble diagram, if you would find all components of the matter of the universe, would add them, and if this quantity would be larger than this quantity, you would get the geometry should be the geometry of three-dimensional sphere. If these two quantities are exactly the same, then space-time is curved, but nevertheless space at each moment of time, okay, taking this natural foliation, has Euclidean geometry. In case when the amount of matter is not enough to close the universe, you have hyperbolic geometry. Now cosmologists or astrophysicists or whatsoever, where is to clean, because I can do it with my hand, but I thought that there is something here. Ah, I found it. You see? So, you see, cosmologists introduce so-called cosmological parameter, omega, which is defined like energy density to critical energy density. This quantity characterizes, as I say, the kinetic energy of the Hubble expansion. This quantity characterizes the potential energy of self-gravity. Now, you see, of course, this is time-dependent function, but if it's smaller than 1, then it always will remain smaller than 1. Now, if omega is larger than 1, it would mean that you have closed universe. If omega is equal 1, it would mean that, as I said, you have flat universe, k equals 0, and omega smaller than 1, hyperbolic universe. If in 1980 you would tell astronomers that omega is equal 1, they would think that you are crazy. Because at this time, nobody from observation could whatsoever get more than 0.2. Even 1997, okay, people who were doing this virial dynamics of the clusters were claiming you can never get more than 0.2. Or 0.3 was the maximal thing. Then, okay, if it would be the case, then, of course, what now people know as inflationary universe would be killed immediately. Some of my friends has not so good nerves as me. So, okay, 3 years before they started to write all the papers involving all this kind of crap called open inflation. Now they don't want to recall it anymore. But, okay, I recall my telephone conversation with a good friend of mine. He told, are you going to give up on this thing? I told, but what can I do? He told, no, I will never give up. For me, everything was proved 82. You see, it was actually a bit ridiculous thing, because science is not like love, okay? You cannot stay in love because of your principles in science, yeah, with some theory. If theory is ruled out, then it's ruled out. Of course, no theory can be ruled out completely, because you can always add couple of parameters, and for author it's always alive. I am sorry, David, for making this trivial statement, because somebody, when I was teaching in Vienna, told me, oh, okay, thank you for telling us, okay, how should we do science? I told, okay, I'm not telling you because you know very well, okay, you were at the time when people were building bombs and they knew what does it mean experiment. But, okay, new generation somehow is spoiled by this blah, 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 as you understand. You know, I'm not in this sense hope in wrong auditorium. Of course, it doesn't mean that you have to couple everything what you do with experiment directly, because then the life become boring. Yeah. Now, next thing, what kind of equation of state can we have in the nature? First of all, as I said, dust. We are all dust from the point of view of general relativity. Second thing is 1/3 of energy density. This kind of equation of state you have for photons and for all ultra-relativistic particles. Now also we have discovered so-called dark energy, for which equation of state pressure is equal minus energy density. Can we imagine some microscopical reason? Not necessarily that it should be this reason, but can we imagine some microscopical reason to justify this equation of state besides of introducing cosmological constant? Of course, take scalar field. Scalar field is boson. Therefore, in distinction from fermions, even for gravity, okay, it's relevant that it's scalar field, because you can put this scalar field in condensate, or better to say, make homogeneous scalar field, which will not destroy isotropy, you see, in distinction from vector field. And then the energy momentum tensor for this scalar field is, as you know, phi mu, phi nu, minus 1/2 delta mu nu, and then here you have phi gamma, minus v, where v is so-called potential. And this energy momentum tensor is written just requiring the condition that if you will take covariant derivative here, you have to get what people called Klein-Gordon equation, v phi is equal to 0. Now, okay, you can notice immediately that if you will introduce, if phi gamma is larger than 0 in my signature, and it's always larger than 0 for the homogeneous field, which is time varying, that this energy momentum tensor can be rewritten in the form when it precisely looks like hydrodynamical fluid, u nu minus p delta mu nu, where epsilon by definition is 1/2 phi gamma plus v, and p is equal 1/2 phi gamma minus v. These things means derivative. You see, then for velocity is just gradient of scalar field normalized by this quantity, and it's all. So you understand that this kind of condensate also can be considered as hydrodynamical fluid. And what kind of equation of state can be there? Take homogeneous field when it depends only on time. Then all these derivative become time derivative squared, and this thing becomes again time derivative squared. So energy density of scalar field is the sum of kinetic energy and potential energy, and pressure is the difference. Now, if I will manage, okay, to, for instance, manage to have some kind of conditions like phi dot squared is much smaller than v during substantial time interval, then I can forget about these two terms, and you are getting equation of state pressure is approximately equal minus energy density. Okay, when you are normally satisfying this condition during long time enough interval, when kinetic energy much smaller than the potential energy, you say that you have slow rolling scalar field. Okay, condition I will write later. And in this case, scalar field mimics U cosmological constant or explain U dark energy. But as I said, maybe we don't want to have this eternal cosmological constant in spite of the fact that all the data now are in perfect agreement with p equal minus epsilon. But you know that there is always accuracy. And I have nothing against if this cosmological constant will decay in 100 billion years. Okay, I don't care, honestly speaking. But okay, so all equations, by the way, also this scalar field in the stage of oscillation can mimic the other equation of state. If you will take, for instance, scalar field, which is massive scalar field, so with potential proportional phi squared, then during the stage of fast oscillations, when frequency, which is determined in this case by the mass, yeah, is larger than inverse cosmological time, during the stage of oscillation, this scalar field with this potential mimics dust with pressure approximately equal 0. Now, if you will take lambda phi 4 potential, again, we'll consider the stage of fast oscillation. Then for lambda phi 4 potential, pressure is approximately equal 1/3 of the energy density. These things are not distinguishable from the point of view of gravity from real radiation or ultra-relativistic particles, and they are not distinguishable, for instance, from dust. And when people speak about ultra-relativistic equation of state and entropy, yeah, I am sorry, here I have zero entropy, but nevertheless ultra-relativistic equation of state, and all the structure of the space-time to be the same as if you would have temperature. Therefore, all these kind of things, when people try to relate, to derive too much thermodynamics from general relativity, I think is exaggeration a little bit. Because conformal structures also take homogeneous scalar field, zero entropy, right? Condensate. Equation of state the same as ultra-relativistic. And horizons, everything is the same in the universe, which is filled just by scalar field. Now, okay, I still have few minutes to say a little bit more.
It's a good time for a question.
Yes.
You described the Newtonian way to get the equations of motion.
Yes.
And I suppose we can think of it as a kind of a pseudo-Newtonian limit for cosmology. And the question is, can you extend it to a full perturbation theory in such a way that, for instance, the perturbations can also be described in a semi-Newtonian or
Yes, inside horizon there is extra condition. Inside horizon, inside the curvature scale, and also only when pressure is much smaller than energy density. In this case, of course, you have perfect Newtonian perturbation theory. You can derive it either from general relativity or you can derive it from Newtonian theory. Order by order. But no, but okay, next order, of course, is different, as you understand, because general relativity is different from Newtonian theory by all these corrections.
That's my question. Can you take general relativity and expand it in a post-Newtonian way?
General relativity you can, but post-Newtonian way you can do, right? But for very limited class of problems. When, for instance, you are considering clusters of galaxies, you can do it. But when you consider CMB fluctuation on the scales large, which are formed on the scale larger than the curvature scale, you can forget about it. You see? So now, so what are the solutions, okay? 5 minutes, I think, is enough for solution of these couple simple differential equations, yeah? So, first of all, okay, solution of this thing. Minus 3 a dot over a epsilon plus p. Let me consider, just keeping in mind practical purposes, only useful equation of state when p is equal w energy density, where w is constant. And this w is equal 0, 1/3, or -1, or approximately -1 for 3 particular cases. Then from here, if you substitute this thing here, you will get immediately first integral that energy density is proportional 1 divided by a in power 3, 1 plus w. Then it's clear that w is equal -1. Energy density is constant as it should be, because here you have 0. Now, when w is 0 for dust, it's 1 over volume, as it should be in case of conservation of mass. For radiation, it's 1 divided by a in power 4, because number of photons, for instance, is conserved, but each photon is redshifted. And this is extra factor A. Now let's look what happens with these kind of things in our universe. Here is energy density, here is scale factor, and we live today when scale factor is A0, for instance. You can set it to be equal 1 if you want. So what today we have? We have photons with a temperature 2.73 degrees of Kelvin. You can calculate energy density, which is proportional to the temperature in power 4, and then you will get number like 10 minus 34 gram over centimeter cube, perhaps. I do not know, but much less, 3 orders of magnitude less than energy density in the baryons and cold dark matter. We have baryons and cold dark matter. Baryons plus cold dark matter, both of which have pressure approximately equal to 0. Here pressure is equal energy density over 3. And what is dominating today, 76%, is so-called dark energy with W, with pressure approximately equal minus energy density. This constant, of course, stays also always constant. Now, what happens with baryon and cold dark matter when you go in past? When you go in past, it grows inversely proportional to the scale factor. Therefore, it's clear that when universe was just few times smaller, you can forget about cosmological constant. It started to dominate only recently. This guy is also grows, but it grows even faster, okay, because it grows like 1 over A4 in past. And there is a moment of time when the universe was about 10,000 times smaller than it's right now, and it's called redshift. I will define it later, which is the ratio of scale factor to the scale factor at the appropriate moment of time minus 1. So at redshift, about 10,000, so when universe was 10,000 smaller in a sense, it could be infinite, of course, but all distances were 10,000 smaller, the energy density of radiation was equal to the energy density of the cold dark matter. And more earlier, okay, it was dominating even. So this moment is called equality moment. And near this equality moment, which happens when universe was about 300,000 years old, okay, happens also what is called recombination, when all free electrons are captured by free protons and universe becomes transparent. And this is the time when the whole CMB picture is formed. Now, what about dynamics of this kind of evolution? You can get it very easily, because you can write immediately equation like this one, over a squared plus k over a squared is equal 8pg over 3, and then energy density today A0 over A in power 1, what was it, 3, 1 plus W. Now, to solve this equation, you can solve it very easily. First of all, let's consider only practical case. You know that when Zeldovich and Novikov was writing book in 74 on cosmology, it was 900 pages. Last 5 years ago, when I was writing book, it had more material, but nevertheless more relevant material. It was only 400 pages. And what I did, I took relevant thing from Zeldovich Novikov and expanded and thrown all the relevant thing. You see, in this sense, okay, with the progress of science, sometimes textbooks are shrinking instead of growing. So when you do not consider. So now let's forget about this term. Then, okay, what is A dot over A? Let's cancel A, then you get here 1 over t squared, yeah? Because dot is not cancelled. And from here you are getting immediately that A is proportional to t in power 2 divided by 3, 1 plus W. Okay, so it's all solutions. Now, if you don't want to forget about K, let's look when K is irrelevant. Look, when W is larger than minus 1 over 3. okay, then this term, when you go in past, grows up in past faster than 1 over a squared. Therefore, in past, this term 1 over a squared you can neglect. What does it mean W larger than minus 1 over 3? Look at this equation. W is larger than 1 minus over 3 means that this quantity is larger than 0. Here is minus sign, so it means that gravity is attractive force. So if gravity is attractive force, then in past, for the dynamical evolution, you can always neglect curvature term. In this sense, k equals 0 case is past attractor for all three cases. In decelerating universe, when you have minus here. What does it mean when what you have in the case when W is smaller than minus 1 over 3? This thing becomes negative. Minus here give you plus. Gravity becomes anti-gravity. It becomes repulsive force. This is the case which is known under the name now inflation. Before that, okay, people were calling it de Sitter. Doesn't matter, quasi de Sitter. In this particular case, if you look again at this equation, this term becomes irrelevant in the future when A goes to infinity. Therefore, in the case of the universe where gravity becomes anti-gravity, k equals 0 case or flat geometry is attractor in future. This is in fact the reason for this prediction that if universe in past went through the stage of accelerated expansion, then on this stage it goes to the future attractor, which is Euclidean geometry. And if you will not stand on your ears, you cannot avoid this conclusion. Universe becomes flatter, flatter, and flatter. But now here, you can get all the evolution laws. I'm finishing here, yeah? So in case when you have pressure equal to 0, W is equal 0, then scale factor is proportional to T in power 2/3. In case when W is 1/3 for ultra-relativistic component, scale factor is proportional to T in power 1/2. And in case when W is equal minus 1, scale factor is proportional to T in power infinity. And what is T in power infinity? It's exponent T, right? So and then you have accelerated expansion. Therefore, using this fact, now you could draw very easily, okay, last thing, yeah? 2 minutes. Because I studied, by the way, I counted 3 minutes. No. I had 2 introductions, I am sorry. So, you see, now you could draw the picture of the evolution of scale factor. And scale factor as a function of time is like this one. Today is T0. So there was the moment of equality. And there is the moment when dark matter, and dark energy approximately equals. Here, dark matter, dark energy plus baryons, of course. Then, what we have here? In past, A was proportional to T in power 1/2. Then, at the moment of equality, what we got? T in power 2/3. And when dark energy started to dominate, we are getting T exponent HT, asymptotically, of course. So here, second derivative is negative for the scale factor. Gravity is attractive. Here also negative, but here becomes positive. It is the stage of accelerated expansion today. You see? So this is the dynamical picture, and at this point, okay, I finish. Okay, good.
Let's say
Break. It's okay.
I stopped you because